Hi, everyone. It's great to be here again at the Knowledge Graph Conference. We are right at 3:30 now. Maybe I'll give it just 30 seconds more just to let people trickle in. And I'm really glad to see folks join this session because I think there was some confusion last week, so it wasn't listed on the schedule. The session had been accepted. So, but it'll be recorded also. So folks who didn't get to see this session live will be able to see the recording. I see some more people trickling in, so I'm going to give it a few more seconds. So let me get started now. So once again, it's glad to be here. I work for Oracle. I've presented at several sessions in the last, I think, 3 or 4 Knowledge Graph conference events, and it's always a lively discussion and with experts, and it's always good to discuss with folks, even if virtually. So the topic today that I chose was talking about graphs coexisting with relational tables. It's not a new topic in the sense that if you heard me speak at other events, you might have heard me talk about this particular topic. The reason I wanted to focus on this was I think there's a lot of confusion out there on graph databases, native graph databases, and all kinds of questions around what's the best way to implement graph databases so that graph queries and graph analytics can be done at high speed. And my goal here is to kind of bring to your attention what's the latest in this discussion and highlight all the things that are possible when you work with graphs and relational tables. The point is also when we start talking about native graph databases, I think we start thinking of, okay, these are like silo systems or separate systems. And I think that is hurting graph database adoption. And that's also some of the things I want to highlight today. That when we talk about a new data management system, that can end up being very expensive and not really something that makes it, not something that can be easily adopted in enterprises. So my goal here is to say that you can work with graphs within IT infrastructure that has a lot of other advantages, which I think will be beneficial to the graph community rather than trying to invent some things from scratch. I work for Oracle, like I said, so admittedly, I have a bias on relational tables and the advantages of relational tables. But I really hope to kind of rise above that bias and talk about objectively talk about what are the why we think graphs with relational tables is a really interesting strategy. So many of you might be familiar with Oracle, just in case you're not. I started over 40 years ago and started as a company focused on relational databases, has since evolved over the decades into an enterprise software company. This means we work with many different enterprises across many different industries. Anybody you can think of that has data to manage, they're likely to be using Oracle. So it's got widespread use and it's widely used across many different industries. And over the years, we have acquired or merged with various other companies. We have products. We're no longer just a relational data management company. We have various applications. We work with we have big data platforms, AI platforms, data lake initiatives, and so on. So it's a very large company focused on helping enterprises manage their data and be successful. So with that, here's my agenda. I will start with graphs are intuitive, which I know I don't need to tell this audience, but it's always good to recap and say that, okay, this is why graphs are so useful today. And then talk about why we think graphs should be used with relational tables, or rather, graphs should be implemented with relational tables. And then talk about how we do this. And I will talk about this from a user perspective. So if you're working with graphs in a relational database, such as Oracle, how do you create a graph, query a graph, analyze a graph, and so on. So I'll pause periodically for questions. If you have questions in the meantime and just want to post them in chat, please feel free to do so. So I'm sure, as you've been hearing in this day one of this conference, connections are the key way to get new insights into your data. Data is connected, and when we talk about data in purely relational terms, that is rows and columns, becomes harder to see how data entities are connected, how you can traverse connections, especially when you don't know how long a connection is, and so on. And this can be for data sets that have an explicit connection, like social networks, like who follows whom, who has reposted someone's tweet or post. Those are explicit connections, or implicit connections, such as in a financial transaction system. If I and a friend go to dinner and then I transfer money to my friend using some kind of a payment solutions app, that's a connection between my account and my friend's account because there was an actual cash transfer between these accounts. So financial services industry, and I'm sure many of them are presenting at this event, they want to view their data as a graph because they can get new insights into their data. So viewing data's connections is really powerful. So, okay, all of this we know. They're still sharing a quote from one of our customers that graphs kind of, by seeing the connections, allow you to kind of dig a little deeper into your data and ask questions that you might not have thought to ask before. So graphs are powerful. Once again, it helps us see data not just as rows and columns, but also as a set of connected entities. So really powerful, really cool technology that's has become a very hot topic. So here's are the slides I used to explain to my colleagues on the relational database side, right? Why graphs are intuitive. And I decided to include them here as well because I think it really makes sense and really highlights the things that you can do with graphs. So in the standard table model or relational model, we have columns and rows. So when you ask a question such as, is A connected to F? It takes a lot of SQL queries to answer that question because you have to now traverse, you have to go from A to B, and then go and see where B goes to C, and then C goes to I, and so on. You have to keep following the links in your data explicitly because the links are not there. The links are all kind of buried in the data. You have to kind of write your query so that you traverse these links and say, yes, A is really connected to F. Whereas all of us who work with graph databases know this is really simple to do when you model your data as a graph. It's really easy to follow the connections. You have your data set is represented as entities rather than rows and columns. Your data set is represented as entities and then the connections between them. And then with the graph database, you have the syntax to follow these connections. They can go from A to D to E to G and then to I. So you can actually go follow these connections, and graph databases make that really easy to do. So, and you can keep building on that, right? You can say, okay, is A connected to or you can say is how many incoming connections there are to I. And with the graph query language, the syntax is typically something like this. So I want to specify the pattern where I want to look at the different entities that are connected to I. So in the graph data model, I can also ask questions such as, okay, I'm looking not just as the direct connections to I, but I'm looking at indirect connections to I. So I have this I, and going back to the financial transactions example, if this I is a bank account, I'm looking not just as direct connections to I, but I'm looking at indirect connections. Like somebody might have transferred money to me, then I transfer money to my friend. So this other friend has transferred money to my other friend through me, and that's an interesting connection, and so on. And that's what graphs help you do, as all of us, I'm sure, are very familiar with. And you can keep growing this. You can say, how many hops do I have? And do I have many different parts between the same two entities? I have A, and then I have I, and I have two different parts, or actually multiple parts if you keep looking at this graph. And this is where graphs really shine, finding the different types of connections, finding how long the connections are, and understanding the nature of these connections. So, for example, by nature of these connections here, I mean, let's say I add a few nodes to my graph. And then I have a new node here, J, that is connected to I, but only by a single edge. So I is highly connected. I has three incoming edges and has all these other incoming paths. But there's only one outgoing edge to J. So you can say that I is important because there are lots of incoming edges. And you can say J is not important because there is only one incoming edge. But on the other hand, that incoming edge is from a highly connected node. So I is highly connected. And even if it has only one income, if J has only one incoming edge from I, this still makes J very important because it is connected. It is coming from a highly connected node. Like in a social network analysis, this could be something like saying it's not how many people you know, but who you know. Like if I know President Biden, I probably am in a position of power, even if I don't know a lot of people. So these are the kinds of things that graphs can help you do very well. And this kind of thing, you can run a graph algorithm, and then you can determine that you're working, which nodes are connected to other highly connected nodes, and so on. So graphs are intuitive. Okay, we get that. So now let's get back to the relational databases, like how Oracle started out its journey as a company. It started its journey as a company that was extremely efficient in managing data's rows and columns to do extraordinary things at very large scale, like your bank accounts managed in a relational database, airline reservations managed in a relational database. Does the concurrency bit of it extremely well, right? I can put money out to my account, I can take my money account, and there's no inconsistency. Two people trying to make, or five people trying to make an airline reservation, only one person consistently is able to buy that seat if there's only one seat left. The relational databases do not allow airlines to kind of sell the same seat to multiple people. And then if the aircraft changes while making a reservation and there's suddenly more capacity, that shows up. So my databases do these types of things very well. So now, what happened was there are always new workloads, and everything is not just rows and columns. So there were new data types and new workloads. And graphs and connections are one such example, and they're not the only example. I mean, this has happened for all time. We had XML. In my career, we've seen XML, we've seen JSON, we've seen images. They were allowed, that was and images and audio and video. Even before the smartphone era, that was data that folks wanted to really use in their applications. So there were always new data types and new workloads that people wanted to use. And they're always looking to base their decisions on all the data, not just on their data that was traditionally stored in rows and columns. So databases like the Oracle database had to evolve. They had to evolve to say, okay, how do we now work with all of this data? Images, XML, JSON, medical images, 3D images. How do we work with all of this data? And how do we link that with the data in what was traditionally stored in relational databases? And graphs and modeling connections in data. As a graph is yet another data type. That's the way, at least I see it. And so you want to include that dimension of including connections along with your relational data. So I borrowed this slide from, I recently gave a lecture at Purdue University, and I saw this slide from one of the classes, and I thought it kind of highlighted nicely what we do. So I've credited him here. And basically, it was soon time for databases, like relational databases like Oracle, way back like 25 years ago, to say, okay, we had this nice relational model. Now we had to start looking at this semi-structured and unstructured data. So, all right, that's good. So we know that data is evolving, and the new workloads also, right? There used to be transactional and OLTP systems, widely used. Like I said, any enterprise with data probably is running a relational system. And it could be Oracle or it could be someone else, but they almost certainly are running a relational system. So along with new data types, there are also new workloads like artificial intelligence, machine learning. You want to apply all of that to your data. You want to traverse connections, which is where the graph comes in, and so on. So while we explore these new data types and new workloads and see how we can do these things efficiently, does that mean we have to say, okay, let's forget all the progress that's been done with relational databases? Can we build on the progress that's been done with relational databases and make that work with these new data types and new workloads? That is kind of the, I did close my Slack. Give me a second. I'm just going to try and close it again. And hope that that notification goes away. So can we build on what we have learned over the last 4 decades that relational databases have been in existence, and also use that for new data types and new data models? That's really the question. So let's kind of pursue that thought a little bit and look at, again, what databases are good at. As I was saying earlier, any enterprise which manages data, it's got to have a relational database. It's not possible otherwise to manage. It could be in the cloud. It could be something that they don't even know is a relational database. They're posting something somewhere, but there's a database somewhere which allows them, which is always available. So it's a data management system with the server is essentially always up. And what that means is if a server goes down, there is like a rollover mechanism or some of the load balancing mechanism. Some of the server takes over. You have things like a backup and recovery system. So to a user, it's almost seamless. They're working with the server, something goes down and the server takes over. This is all bread and butter infrastructure in any relational database management system. High availability. Like I hear customers say that all the time. They say, oh, the server just keeps running and running. I don't have to worry about what happens when it goes down. That's high availability. And then concurrency. I have thousands of users who need to access this system, like the airline management system, the age-old management system that you learned in your relational databases class. I am making reservations. It's a holiday season. I have thousands of customers visiting my website at the same time. I need to make sure I'm not selling the same seat twice. It's an old problem, but relevant today. I mean, you always need to ensure that you can have concurrent access and everyone has a consistent view of the data. And in all of this, you have security. You need to manage your data securely. You cannot afford, like me, to log in and see someone else's data. I have to only see the data that I'm allowed to see. You might need the security at a very fine-grained level and so on. And then performance and scalability, we all need this. So this is just an example screenshot from a slide where Oracle regularly publishes benchmark results for various relational workloads. And of course, you have very high numbers of transactions per second. So what's the customer expectation when working with graphs today? So when the graph world started off, there was a lot of focus on graph analytics, like finding the new insights that I was talking about. Is this person important in social network analysis? Is this person an influencer? Or is this particular financial account fraudulent because of the pattern of connections to that particular account? And that was, that was a more, or I would say, an analytics use case. So you can take a snapshot of your data, you can work and do all of this analysis. A data scientist can download a copy of the data onto their laptop, and then they can work with the data in that laptop, and then you can get all kinds of interesting insights because you're viewing your data as a graph. But very soon, in any data management workload, we soon start coming to things like this, that, okay, I have a graph, but I don't want to just take a snapshot of it. I want to be able to constantly update it and use it as a graph. And I have high concurrency requirements, such as 3,000 queries a minute, sessions a minute. So 3,000 people are going to be logging in at the same time. And they'll be running 1,000 to 1,500 queries per second. And I need to traverse my graph. I need to go down. I have this bill of materials graph. To take an example from manufacturing, I need to go down 15 levels or 20 levels. And I need to do this concurrently for large size graphs. And then we have all of the streaming data coming in, constant updates coming in from data streams. If you're using something like Apache Kafka, and you need to then merge this data, as they say. So you need to check whether the data already exists. And if it exists, then you update it. If it does not exist, you insert. So called merge or called upsert, and there are various terms for this. But so these are all classic data management problems. You have a database, you are continuously getting an incoming stream of data, and you have to consistently update your data instantaneously so that the transactions can see this updated data instantaneously. And what has consistently been proven again and again in a variety of ways is that non-relational databases, that's when they start having some challenges. And just to take one example, in this case, somebody was working with lots of Kafka writers, and when they crossed 80,000 vertices in a graph, they began to have problems. It's just because the relational theory has been, not only was the theory sound to begin with, it's just that when they began to implement, and they've been implementing this, all database vendors have been implementing relational databases for decades now. So that the relational database does this kind of thing very well. So very quickly, graph developers were beginning to say, at least in our experience, that I want all of these data management advantages. And then I don't want to think about that. So, but I still also want to do graph analytics. I want to do graph analytics along with my OLTP applications. And I want all of these OLTP transactions to be asset compliant. Like, I want consistency, I want atomicity. I need to be able to say that my data is always valid when working with it as a graph. And this is not the first technology that has run into this. Right? Everywhere, people expect their data to be consistent, even when they're working with graphs or working with images or working with the XML or JSON data and so on. So the challenge now, I think, for the graph community is how can we support graph analytics and graph queries without sacrificing any of the advances made in the relational database world. And I think that's where I think the graph community, in my opinion, should focus on a little bit. Because if they say that, okay, this is this cool new technology, we had to go write all of these new databases that do the specialized graph operations, I think that's where we're losing an opportunity, because developers want these bread and butter features that exist in a database. So, because developers, all they want is to focus on solving problems. They're not interested really in how graphs are implemented. They're not interested in understanding the ins and outs of a graph database. But they are interested in solving problems. In fact, I talk to developers all the time where they don't even want to think of it as a graph. They just want to say, okay, this is connected. I have this piece of data connected with this piece of data, and I want to do X, Y, Z with it. I don't want to sit down and think about, okay, how can I manage my system? How can I have my database system always available? How can I deal with concurrency and security? They just don't want to think about that. These are problems that have been solved. So they really want to focus on solving problems with graphs. And I think vendors like Oracle, I mean, when I say vendors like Oracle, I mean like large size companies, we have learned this lesson from the big data era when there was a similar interest from developers in saying that, okay, Apache Hadoop was this new technology. It solved a lot of interesting problems. It said you could process in parallel large amounts of data. But very soon, when it was very exciting for a while, and then very soon developers began to realize that their IT departments find that there's a high maintenance cost. It's expensive to change because it's very specialized technology. And finally, it did not support writes. It is very good for reading and doing certain things. But when you talk about data management, very soon you need transaction consistency. Very soon you need updates. There's a very small class of problems that's really focused only on reading and then analyzing your data. You want to be able to update. You want the data to be highly available. You want to make that all integrated together. So learning from big data, we really learned the lesson that it's so important to integrate everything together and not view data as siloed systems. And since Oracle has been around for 4 decades, we see this pattern, right? That when there are always new technology coming in. So after SQL, there was this object database. There was this idea of saying, okay, we need to store data on objects because SQL is too set oriented. You're looking at sets of rows, whereas we need to look at object and all the associated properties of an object. And that was interesting for a while. And then what ended up happening was object, some of the features of the object database just became merged with SQL. And then similarly, XML. Then some of the XML features began to be merged with SQL. Some of the JSON features began to be merged with SQL. So we see this as the requirements grow from real world use cases, we see there was a need for object databases, there was a need for XML and JSON, there was a need for big data, Apache Hadoop platforms, and now there is a need for viewing data through connections. But all of them over time go back to integrating with SQL in some way. Because SQL has shown amazing staying power because it does some things extremely well. And it's very hard to just say, okay, I don't want to deal with SQL. I want to only deal with this new language, which does this one thing very well. What about all the other things that we need to do with data, right? So it becomes, so over time, and if you've seen me speak at other sessions, seen me use this slide again, that over time, SQL has shown to be has very, very strong staying power. Like even in the big data world, MapReduce started as this technology. MapReduce was complex, and then people said, oh, we need to simplify. And guess what was the way to simplify it? SQL. You had the SQL layer over files on Apache Hadoop platform. Then people tried to implement databases on top of the Apache Hadoop platform. And finally, all things this kind of coalesced around SQL because SQL is an elegant way to work with data. And databases have all of the strong foundation of all the features that I've been talking about. Does that mean there is no need to improve SQL? Absolutely not. There is every need to improve SQL, and SQL is constantly evolving as well. And that's some of the things I want to talk to you about today. How has SQL evolved to work with graphs, just like it has evolved to work with JSON and objects and so on? So, and I think the graph community would do well to remember these lessons because otherwise I think we just end up becoming a silo. And when I talk about this, often I get the question saying that, oh, but relational databases are slow. And the only way I can traverse graphs in a relational database is to follow these links and following links is expensive when I'm looking at something in a table and column structure, because it's not really conducive for following entities. I just need to follow it. It's too expensive to do that. I had to fall back on joins. Joins are expensive in relational databases, etc., etc. But the thing is, relational databases have also evolved. It's not as though they were standing still, right? When all of these requirements were coming in, definitely Oracle was not standing still. We have added object support, we have added JSON support, we have added so many things to the SQL layer, to SQL as a language, and to the database storage engine and query processing engine. So databases, and it's not just Oracle, many databases have also gotten very good at managing semi or unstructured data, like managing images in blob types, managing JSON using native JSON types, and managing different kinds of data very well. So relational databases also are evolving. And the advantage here is that you can use all of these new workloads and new data types without sacrificing all the stuff that is available in the relational engine for you. All the 4 decades worth of experience that's been built into building a relational database. And this some examples from Oracle that we have implemented in terms of making relational database queries fast. We have in-memory options. We can do fast parallel joins in memory. The recursive with syntax in Oracle, we allow for extremely complex partitioning of data. I should say extremely sophisticated partitioning of data, where you can work with data in a highly parallel way, which makes a lot of sense. As hardware gets cheaper, we have our own engineered systems as well, which allows you to do this at extremely high speeds and high level of compression. Because finally, the reason any database is slow is you're reading from disk, right? You have to read from disk, and tends to be the most expensive operation. So compression, partitioning, all of this minimizes the amount of data you read from disk. So to make these relational operations extremely fast and enable relational engines to work with new types of data. And I want to call out one specific innovation from Oracle, which is to scale out to the storage layer. So, or filter at the storage layer. So what that means is, like I was saying, IO is really the single most expensive operation when you're reading data from the storage layer. So if you have a filter there that says, I only want to read the data that I need, that actually speeds up your operations a lot. And it is very useful for various kinds of workloads. So databases have been growing, and the databases, in addition to having the advantages of high availability and concurrency and transactional consistency, also are good at some types of queries. Any query that involves a set of data, like set of rows, like thousands of rows, and you do an operation across these rows, like I want to aggregate across these rows, or I want to take all of these rows and feed them to another part of the application. Anytime you're working with a set of data, relational databases are very good at that. So in graphs, one of the things you need is pointer-based traversal. So you need to traverse from entity to entity to entity. You need to do that efficiently. So rather than starting with a way where you can do that traversal very efficiently and then try to build out all the infrastructure, I believe what the approach relational databases should take is build on all the existing infrastructure that a relational database has, and then add fast pointer-based traversal to it. So in other words, everything is technology is always evolving. So take what really works well in the relational engine, keep all of those features, and then add these pointer-based traversals to your database engines, so that you're not sacrificing what works extremely well. Like when you have a high cardinality, a lot of data movement in intermediate steps, you're not slowing things down. I cannot tell you the number of customers who try a native graph database and then come and say, okay, it did not scale beyond a point. We would like to look at what Oracle has to offer. So because there is a reason why Oracle and relational engines in general can scale well for certain types of queries. So we don't want to lose all of these these things as well. So as we have evolved also, we've really learned that it's a lot simpler to manage data when it's not fragmented. It's a lot easier to manage data when it's all integrated together. Like if you have a specialized graph database or a specialized JSON database or a specialized document management database, it's just multiple databases to manage, and it's hard to work across all of these different databases. So instead, again, it's not just Oracle, other relational engines are following this as well. Let's see whether we can integrate all of these different data types into one database. So again, the developers can focus on getting the job done and not worry about managing it, keeping it available. All of that will be managed by standard database infrastructure. And this is just a slide that I also liked. This is one of our executives had used, as we used to have all of these specialized databases, and we used to have all of this, not, I'm sorry, not specialized databases, specialized devices, right? Every time we had a new device, like cameras became digital and cameras were cool. And then way back, I think we had this, I forget what they were called, the Discmans, where you could listen to music on the go, and that was a great innovation, and so on. And then after you have smartphones, right? And next time you need new technology, you're not going to go and get something go and create something separate once, but there's going to be new requirements. You're not going to create something separate. You're just going to see how the smartphone can evolve. And that's what happens every time there's a new need for an app. The smartphone evolves rather than a whole new device doing something special. And that's kind of how I think it is with relational databases as well. Relational databases used to do one thing very well, and then there were all these other databases that were doing things very well. But now I think we are at the stage where this one database engine can do all of these things very well together, and that engine is going to evolve as there are new requirements. And all of this basically simplifies, reduces complexity, reduces operational costs, minimize risks, and all the things that enterprises like, that the chief data officers like, because it reduces the risk, reduces their costs. They don't have to worry about new technology. They can work with existing technology, with existing skills, which has evolved. So it's like taking a cell phone and buying a new version of it that has all these other new capabilities, rather than trying an entirely new device. And this is really one of the main reasons why I think graph databases should become an integral part of relational databases, and that's when you will get wide adoption. So that's the why, and then I'll talk about the how, and then that will, out of because I'm most familiar with Oracle, that's it's going to be focused on Oracle, but I am going to talk about some of the SQL standards and so on. And so hopefully I'll be able to be a little removed from Oracle. So I'm going to pause here and see whether there are any questions. I don't see any questions in chat per se, but let me pause and see whether anyone wants to put in a question. Well, if not, I'll keep going. So we looked at the why relational databases, or rather why graph should work with relational databases, or rather I should say why graph should be a part of relational databases. And now look at the how and how we do it in at least some organizations. So I'll start with an example. So going back to the financial transactions example, this data is almost certainly stored in a relational table somewhere, right? When I'm using a payment solutions app to transfer money from my account to my friend's account, there's probably a table that has information about my account and the money I have in the account and everything. And then when I make a transfer, the amount is deducted from my account and then added to this other account. And so it's really fundamentally a relational transaction. It can be done so simply with relational databases that why would you ever want to change that? But now I also want to do graph analytics on this set of tables. I don't just want to do my standard relational queries of checking, okay, what's the account balance here? I also want to follow connections. So when we have graphs with relational tables, how can I follow such connections? Because I want them all, I want to be able to view my data as a graph. So, and when in the financial services industry, we see these are the reasons that they want to model data as a graph. They want to see whether money is moving around in cycles, like A transfers money to B transfers money to C transfers money to D, and D transfers money back to A. Is there a cycle? Is there such a cycle? Which accounts have suspicious patterns with respect to incoming and outgoing money flow edges? Which are the accounts which have a lot of money flowing through them? Which are the accounts that have an unusually high number of cash transfers between them? So these are the types of questions that can be really best answered by a graph, because you don't know how long your paths are, and you're really looking for connections, you're looking for new connections, you're looking for how the existing connections come together to form a pattern. So financial services industry have their data primarily in relational tables, and then they want to use graphs to answer these questions. So they use the property graph data model, which is one of the graph data models that are in use. And they say, okay, we want to represent our data that's in tables as nodes and edges. So I want to say, okay, let's say I have an accounts table, which has all the account holders and the balances that they have in the bank or in the institution. I want to represent every account as a vertex. And that gives me the ability to say, okay, every account is a vertex. And when there is a cash transfer between two accounts, that's an edge. So I have the information in the transactions, in my transactions table, as to who transfer money to whom. I can take that and I can model that as an edge. So I have vertices representing accounts and edges representing transfer of money between them. I had all of this information in my tables. It's not new information. I had the accounts table, I had the transactions table. Now I just want to view my data as a graph so I can ask other questions. So as you know, in a property graph, once you decide which are your vertices and edges, and in any modeling exercise, whether or not you're starting from relational tables, you will then decide whether your vertices and edges have properties and so on. So, and you can have many different kinds of vertices and edges in one graph, which also makes graphs powerful. So I want to take my relational data and I want to kind of map that into a graph, because I want to do all of this graph analytics. So let's see how that would work. So I have here two tables, bank accounts and bank transactions. And as I said, every row in the bank accounts table could be modeled as a vertex. And every time there is a cash transfer between them, which is represented in this table, the bank transactions table, like there's an account transfer from 1 to 672. So I can go from vertex 1 to vertex 672, and I can model that as an edge. So I can see here that these implicit connections that are in the data, that they're stored in tables. I can take these implicit connections and make them explicit and represent that as a graph. So it's building on this relation table, but it's making explicit some of the connections between these different entities in this row, and then and building that up as a graph. So I can keep building my graph this way. Every row here is a vertex, and every time there's a relationship between them that I'm reading from this table, that becomes an edge, and I quickly build up my graph. So in our product, what we say bank accounts is a vertex table, and bank transactions is an edge table. So what we ask our developers to do is to say, when they want to create a graph from their data, they have to specify what is a vertex table, or which are the tables that are vertex tables, which are the tables that are edge tables, and then behind the scenes, we will do the rest. We'll connect them, and we'll give you a way to traverse all of these links. And the syntax for specifying the vertex and edge table looks something like this. That you can create a graph, you can list the vertex tables, bank accounts is listed as a vertex table, you can list the edge table, the bank transactions is listed as an edge table, and you specify the source and destination and so on. The key point here is this graph model is like a view over relational tables. It is not copying the data. It is not moving the data anywhere. It's like a view. And that in itself gives us all the advantages of the underlying transactional system without us having to do anything. We don't have to implement this transaction system in a specific graph database that is set up to chase or to go after pointers, like to traverse data. We can we can build on the relational system that already has all of this infrastructure and say, now I want to create a view, a graph view of this data, and then I can traverse these links in my graph. But I'm building on this existing relational structure, and I have so many innovations in the database that I don't have to worry about the performance as much as I used to before. And that's the crux of what we offer when we offer the property graph feature in the database. So you can start with a table like this, and you can, when you execute a statement like this, the create property graph statement, you have a graph. And this is what most of us are familiar with in terms of a graph. We are looking at different vertices and how they're connected to each other. So we can start asking business questions such as, which are the highly connected accounts? Which are the accounts that are connected to each other in a cycle? Are there paths between two accounts, and so on? So these are the graph questions that you want to ask with the graph query language, graph syntax. But it would be good to really ask these questions of data that is in your database, because you're almost certainly your financial transactions are sitting in a relational database somewhere. And you want to be able to create a graph from those relational tables without having to move that data anywhere. So by creating a graph model, which is like a view of your data on over these tables, you're able to ask graph questions. And that's one of the one of the things that I mean when I say graphs with relational tables. Your data happens to be in relational data, create a graph from it, so you can have graphs with relational tables, which gives you a way to do all kinds of interesting things with your data. So just to emphasize once again, what we're aiming for is creating property graph view over data and relational tables. There is no data copy, data remains in place. And this is why we get all the transactional consistency and asset properties available for all the graphs that we work with. So you can query this, you can read the graph, you can also insert, update, and delete at extremely high speeds, just like you have in the TPCC benchmark. You can have extremely high speed inserts and updates, and also have 3,000 sessions simultaneously accessing the database, and it will work just as it has always worked for banks and airline transactions and retail folks. It will work just as it has always worked, because it's building on this infrastructure, but also giving you the way to traverse links in a graph. So let's see how we can traverse links in a graph, because now we need a way to specify this syntax. So in a graph query language, and I'm sure there are many sessions on the graph query language, I think there's a parallel session here going on now on Sparkle that I saw. Sparkle is a standard from the W3C for querying knowledge graphs. On the property graph side, the standards are evolving, and I'll talk about one particular standard that is about to become part of the SQL standard. So when we're running queries, so I talked about creating a graph, and it's okay, nice to create a graph from relational tables. And how do I query them? How do I have the syntax to specify these graph queries? So we did two things. We worked with the SQL Standards Committee to include in SQL the ability to write graph queries in SQL. And that's the standard that is coming out. But it's not here yet. It's in draft form now. We're expecting to be published later this year. And we are implementing that in our upcoming, we're planning to implement that in our upcoming database release. So we worked closely with the SQL Standards Committee to integrate that, because again, we really believe that the graph should coexist with relational tables. The easiest way to make that happen is to have one language for both graphs and relational tables, so that graphs are not this separate siloed thing. So we extended the SQL language to do that, and I'll show examples of that. Meanwhile, the standards take time. They take 3 to 4 years. So meanwhile, what do? We created the property graph query language. It has an open source parser. And it's a very SQL-like language, in the sense you have the select clause, you have the from clause, you have where and some and average, and all of those things will work. And in addition, it has the graph syntax, this thing in the middle here, the match clause here in kind of the yellowish color. That is the way to specify the syntax of a pattern. When you're looking for you're querying a graph, you're looking for patterns like cycles or paths or highly connected vertices and so on. And you're able to do that with the match syntax. So we created PGQL to be very, very aligned with the emerging standard, so that we said we'll have SQL-like constructs and we'll have this extension for the match clause. And this extension, this match clause, is what is going to be part of the standard of SQL 2023. So what we did was we created this language to be SQL-like, so they could work with other structures in the database and also with other tools in the database. But it is still a separate language. I mean, PGQL is not SQL till we implement the changes coming in the standard, the updates coming in the standard. It is a separate language. So we had to do some work to have plugins like SQL Developer is a very popular tool for folks working with Oracle database. So we have a plugin, so you can use SQL Developer to run PGQL queries. And similarly, various other tools can also run PGQL queries. So we really worked hard to make this as integrated with the database as possible, which also gives us the advantage of using existing database functions in your graph query language. So PGQL is a graph query language, and the database already has functions such as parsing a JSON document using the JSON value function, or using the contains operator to search through a lot of text. So if you have a lot of text in your graph query, if you have lots of JSON data in your graph query, you can, in your graph query, include JSON parsing, include searching through text, and so on. And once again, these things already existed, right? If you're just going to a completely new separate native graph database, you'd have to start from scratch to implement all of this. We instead think the community should build on the existing engines that work very well for some types of things and add graph to that, which is the approach we have taken. And in RDF graph queries, for which there's a very mature standard, Sparkle, there also our strategy was always to work with Sparkle and SQL. So not say that it should not be Sparkle or SQL, it should be Sparkle with SQL. You can run standalone Sparkle queries using our graph feature today in Oracle database, and that'll work fine. You can run Sparkle queries. You can also run Sparkle in SQL. So here you can see here the lines in brown, we have encompassed a Sparkle query using SQL. So once you run Sparkle in SQL, you can take this data, you can run set-oriented operations, you can pass this to other queries that require a table as an input. You can do so many things when you integrate SQL with Sparkle, so with the standard. So because Sparkle already emerged as a standard for RDF knowledge graphs, that's the approach that we have taken, that you're wrapping that syntax in SQL. But on the property graph side, we have worked with the standards body to really come up with extensions to SQL. And we'll see some examples right here are coming up some examples of property graph queries with the new SQL PGQ standard that's coming out in SQL 2023. So going back to our same example of bank accounts and bank transactions, if we were to create a graph from these tables, it would look something like this. And it's very similar syntax, if you remember from the other slide, in the sense that you create a bank graph, you specify the vertex tables. Here the bank account is a vertex table. You specify the edge table, bank transfers is an edge table. So it's very similar. So you can see here that when we wrote PGQL, we very deliberately aligned it with the standard. So it's very similar. It's very similar to what you saw earlier, but it runs in SQL. So this is SQL. I don't need any tool. I don't need any other client-side parsing libraries. In my relational engine, I can run this statement, which is SQL, run it against tables that I have in my database, and create a graph. So that is the goal here, to have graphs really live with the relational data. So, and just to explain the syntax a little bit, you have the bank graph here. So when the SQL 2023 standard is out, you'll be able to do things like this. Just like you can create a table, You can create a view. You can create an index in a relational engine. You can also create a graph. Graph is just any other data object that is built into a standard database engine. So we have the vertex tables, we have the edge tables, and then we are listing every column. So I mentioned every row in the bank accounts table becomes a vertex. So every column typically becomes a property for that vertex. So and so on. So you specify for each edge the source and destination vertices. But the really powerful thing here is, especially after the standard is available, you can, again, I'm just repeating myself here, you can, just like you can create a table and create a view, you can create a graph. And that is really powerful in SQL. And here's the syntax for querying. So you can see here that the match clause syntax is pretty much similar. You will see this in any other graph query language. I think most vendors agree on that is the way to do this, in the sense that your vertices are represented by parentheses, edges are represented by square brackets. So all of that is very similar. And what it is wrapped around is a SQL, because you have a select account ID that's very much SQL. There's a graph table construct, and all of this is part of the standard. So you can say, okay, I want to find all accounts that transfer money to another account. You would write a query like this. And here are just some more examples. I want to find all accounts that transfer money to other accounts over 1 to 3 hops. So not just direct transfers, but over 1 to 3 hops. So that's what this query at the bottom says, meaning you're going through intermediate accounts. And this is welcome by SQL developers. And I think this is really also the way to get widespread graph adoption. Instead of asking SQL folks to learn a new language or learn a new database and say, okay, here's what you have to do to work with graphs. If you give them the tools to work with graphs within the technologies that they're familiar with, like SQL, they will start seeing that you can really use SQL to write succinct queries. Like here, I have something which says, I want to find, again, the source, all accounts that source has transferred money to, that goes through 1 to 3 intermediate accounts. If I have to write the same thing in SQL without this new syntax, it would be a long SQL query. But the new SQL syntax for working with graphs makes it possible for me to do this more succinctly. So this will give the relational developers also the power to use graphs for something. So we are not just looking at specific graph use cases. We are saying for bread and butter data management issues, you can use graphs. Maybe you can use graphs to debug better. Maybe you can use graphs to really understand a performance of a query by modeling all the modules it goes through as a graph. So we want the graph to be really integrated with the rest of with the relational technology, so that you can leverage and build on all of those usage of relational technology to create new graphs. And here's another example where I'm going again from source vertex this time I'm going to another source vertex, about 0 to 5, about 5 hops long, exactly 5 hops long. So these are looking for cycles. This is looking for a cycle between vertices. The source is a vertex variable. It comes back to this source. So I'm looking for cycles that are start and end with the same bank account and go through 5 intermediate nodes. And again, you can see it's a very SQL-like query, and you have this match clause, which helps you specify the graph pattern. And you could really combine these things with the relational table very nicely. First using PGQL, but also when it's with SQL, you can do this very nicely, because the graph query output, when you run this select on this graph, the graph query output is actually another table. It can be another table. And then it can be combined with other relational tables. You can just do joins on a graph query result with other tables. And this thing about how powerful that can be. And you can also use this with existing features in a database, like geospatial analysis, JSON, time series, streaming. A modern database like Oracle will have support for all of these technologies. And if you're able to have graph as well, you can integrate graph with all of this. So my repeated message here is graph should not be a separate silo. They should work with the system that everyone is familiar with, like the relational system. And here are examples of doing this with JSON. So I'm creating here a property graph called my graph, and I'm specifying the vertex tables and the edge tables. And in the vertex tables, I have a particular column in my table has JSON data. So because you've integrated, I can use the JSON dot notation that's already available in the database to pull out the relevant pieces of information that I want to include in my vertex table in the graph. Like I don't have to create everything. I don't have to dump out everything and have all of this complex filtering. I can just say, this is my vertex table. And for each vertex, these are the columns I'm going to pick up as properties. So and I'm using JSON here to kind of the JSON syntax to reach in and get the right properties. And that's where the integration becomes really interesting. And I have one more detail coming up. All right, here at the bottom here, you're selecting a JSON value and you are finding the key value pair, the value associated with the key name. So I'm taking results from a graph and then using the JSON value function to parse it. And I can do all of those things right where the source of the data is. And here again, I've created a graph and I'm querying this data, the JSON value of this data using the JSON parsing functions. So again, the graphs are not separate from JSON. You can use JSON documents in graph and so on. And another question we get repeatedly is, I have my data in JSON, how can I create a graph from it? So let's look at some preliminary performance numbers, right? I was saying all of these innovations in the database is just doing great things. So the proof is in the pudding. So we had to look at some performance data. We have to do more testing before we publish the benchmark. So these are just preliminary numbers. So we ran some benchmarks on the LDBC benchmark data set, which is 28 million vertices and 177 million edges. And we ran the LDBC short and the LDBC interactive benchmarks. And I know they have not certified the results or anything. I'm just saying LDBC because that's where the data came from. And the key point is these are the kinds of queries that we think will be used in an OLTP system where you have rapid updates and you need the graph to reflect the updates. So not in a graph analytics system, perhaps. So that's why we chose these benchmarks and not the LDBC BI benchmark. So, and the initial numbers look very promising in respect to how fast these queries can run. So, and that's what we're aiming for, the ability to use graph with a relational engine, with relational tables, without sacrificing on performance. And as I was saying earlier, the graph databases have evolved relational databases have evolved so that you no longer need to sacrifice anything when you work with graphs in your traditional relational database. So I'll pause here to see whether there are any questions. Okay, if there are no questions, I'll keep continuing. So we talked a lot about graph patterns and graph queries and so on. Graph analytics is another very powerful feature of working with graphs. So when you have graph analytics, you want the ability to run an algorithm like PageRank. Like you want to identify how connected vertices are to each other. You want to kind of analyze the entire graph and then come up with how the graph structure is, how the vertices are connected to each other, and which are the highly connected vertices and so on. So graph analytics also is very powerful. It's not just querying, it takes the entire structure of the graph and then computes numbers from it. So there are many, many different graph algorithms in graph theory, detecting communities, identifying important vertices, identifying the topology of a graph, doing graph machine learning, another hot topic. So you have machine learning, and then you have graph, and then you have graph machine learning. So there are many different algorithms that can be used. So when you get your graph model created, that is, you create this graph view of your relational data, you can query the data, or you can also run algorithms. But how we run algorithms is also interesting. Because algorithms tend to be complex and not really oriented towards, like I was saying, set-oriented operations. They're kind of a different kind of operations. So what can we do to make that easy to do? So first, let's look at the business problem that this solves. So we had the earlier queries on patterns. what happens here is we can see that 259 is highly connected. So we want to see which are the nodes that are connected to other highly connected nodes, not just 259, but any accounts that are connected to other connected accounts. Like 581 here is connected to 102 because 102 is a highly connected account, and then 102 is connected to 259. So these kinds of graph structural analysis can be done with these algorithms. And what we do is currently we have a specialized graph server that loads the graph into the graph server to run in memory at extremely high speeds. And we're planning on work to move more and more of that into the database memory rather than having a separate in-memory process. But this is what it is today. They do tend to be compute intensive. The graph analytics algorithms, because many of them go recursively over different parts of the graph. So what we have today is you have your database and you load this graph into graph server. So you're taking a snapshot of the data for doing analytics, and then you process the graph in memory with analytics, and then you can use the results anywhere. So this, we did some performance benchmarking on PageRank using the graph server, and it shows that as you increase the number of cores, we're able to exploit the natural parallelism in the graph and like bring and have really good performance for running the PageRank algorithm. Even as the graph size grows, we are seeing a very good performance, and as we increase the number of cores as well, we're seeing very good performance. But this is not a relational database. This is a specialized graph server, and we, like I said, work is ongoing to bring some of that into the relational database because, like I was saying earlier, it's easier to have an established technology to evolve in the direction of new things that are required, and the graph server features are some of those new things. So today, if you're using Oracle database, and now I realize I'm getting more and more Oracle, but I think this is my last but one Oracle slide. So when you're using Oracle today, you have this database. You can create this graph view of your data. You can query the data, and then when you need to, if you want to run some of the algorithms, that's when you load the graph into graph server. You can use the Java or Python to interact with these algorithms. And so we have had this support for a long time, 12.2, and in 23C, like I was saying, we're planning to implement the SQL extension for graphs. So we're very excited about that. So some customer examples. And these folks are using graph server because we don't yet have the graph analytics algorithms in the database, but like I said, we're moving in that direction. So Kesha Bank wanted to analyze their customers based on their activity, like if they swipe their credit card in the same eating establishment within a few seconds of each other, maybe they're friends or maybe they're colleagues who went out to have lunch together. So they use this information to build out this graph of how their accounts are connected, because they want to know how best to recommend products for other customers by looking at how well how the graph is connected and which are the two entities or two customers who are highly connected so they can make good recommendations. So they use a lot of the graph algorithms capability. They create a graph view in the database, and then when needed, they load that into memory and run graph analytics algorithms. Another example from manufacturing is they have data across different domains, and they needed to create a digital thread across many different data components that are reused or have a dependency. Like in this case, they have A1 has a dependency on C4, or A2 has a dependency on B3. So in manufacturing, while analyzing their inventory and for other use cases, this is very important to know how different components in different databases or different silo databases can actually be connected to each other. And when we were working with them and we created the property graph view, you could just see, it suddenly occurred to them that, oh, wow, we don't have to move the data. We don't have to copy the data. Data remains where it is, and we're just creating this view on top of it. So they were really happy about that because you run into a lot of organizational issues if you want to move data around. It's almost impossible. But they're able to create a graph model on top of all of that. And then finally, I think graphs can help the database folks, relational database folks, solve problems with graphs. Like I think I mentioned one or two of them earlier. When you have a lot of let's say you have a query execution, you want to see which modules are touched and which modules the query is going through, that can be modeled as a graph. And there are many, many different problems that will make the SQL developer's life easier when graphs coexist with databases. And one of them is tracking privileges, which can get confusing very fast because you have users logging to a database. You have roles that they have, like what can they do and what can they not do. And these roles are given privileges, as in, okay, I want the privilege to access a table. And where it gets confusing is roles and privileges are used interchangeably and given interchangeably. So if you want to look at exactly what this graph would be, you would identify the vertices. The vertices are typically the roles, the users. I mean, these are the kind of the things in your data. The privilege and the table information. And then what are the edges? The edges are that a user, Scott, is connected to a particular role, or a role is connected to a particular role, because roles can be given to one role can be given to another role. A user has privileges, and there are roles also have privileges. So you see here I have an edge. So users is a vertex, roles is a vertex. I have users connecting to roles. I have roles connecting to itself. I have users connecting to privileges. I have users connecting to privileges for a table, and so on. So this is a graph. And by giving this graph technology or graph techniques to somebody who's worked with relational databases for a long time, they can come up with various different ways of solving interesting problems like this by modeling the data as a graph. And I think this is where it really helps the database community, the graph community, to really bring about widespread adoption of graph technology. So I just took these tables that I have here, and then when I model as a graph, it looks something like this. Right? You have users, you have roles, you have tables, users have roles, roles have roles, roles have access to tables, users have access to tables, and kind of creating this graph helps you kind of unravel the connections between tables more easily. And that's what is kind of missing today in relational tables. And like I said, rather than creating a whole new ecosystem of a graph database, the approach we have taken is to add graphs to existing relational tables, so you can get the advantage of graphs with when working with your relational data. And that's exactly what the new SQL standard that will include support for graphs will help us do well. So here's a query that you can ask where you want to say, okay, find me all the roles that a user has. So you can go through a complex connection of roles given to other roles and so on. I just want to find out all the roles that a particular user has. So, and that can be done with this. So that brings me to the end of my what I wanted to say here. And here are some resources that are available if you want to learn more about how you can use graphs with relational databases. We have a product, it's available for use. You can just use a free edition to get started in the cloud or on premises. And we have blogs and Medium, we have lots of customer use cases, and so on. And I think the one point the key takeaways that I want to make is the graph should not be their own silo. And I think that is, detrimental to the adoption of graphs. Graphs have to be integrated with other data management ecosystems, and the best data management ecosystem out there is a relational database. So that's really the best way to bring about widespread adoption of graphs. And in summary, we're looking, the summary really, I've oriented this towards more what IT folks are looking for. IT departments and enterprises, I mean, they don't want to deal with new technology. They want to lower risk. They want to lower the development effort. They don't want to learn a whole new database. They just want to use the familiar SQL tables and column structure that they work with all the time, and just learn how to create a graph from it. So in that context, I think I had one more slide. Do I have that slide here, or did I? Okay, I just want to talk about this. the graph debate. There was recently a graph debate, I think in March, a couple of months ago, about is there real value in creating a brand new graph oriented database that is focused on traversing links, or should you just have a well architected relational database and you can do the same thing? And there are pros and cons. It's an interesting discussion to look at. And I think the result finally came down very narrowly, 50-50. So I think really, and lots of folks have made really good arguments about why graphs should be built on relational databases. And I just added a few discussion points here today. I was highlighting some of the discussion points here today. And I think this is really the thing to keep in mind, to not be, I guess graphs should not live in their own silos. I think that's the message that I keep going back to. So all of this, all the technology that I talked about, all the query examples that I showed, all the graph analytics examples that I showed, are all included in Oracle Graph, which is a feature of Oracle Database. Any Oracle Database edition that's out there has Oracle Graph on premises or in the cloud. It have a comprehensive support for graph query and analytics. I talked about PGQL that we have today and the plans for the SQL standard that we helped develop. And in the cloud, in our autonomous database offering, we have more automation, automated tools, and we have an integrated notebook with advanced visualization and so on. So that brings me to the end of the session, and I had a good time talking about this, and I hope you did too, but I don't see any questions, so that always makes me wonder when there are no questions at all. So, or please share comments about what you thought about the session. Well, if there are no more questions or comments, I would say thank you very much for joining me here today, and feel free to send me a message on Slack. And I welcome any challenge. I think we only get better when we ask questions, and we really we want to be pushed, and we want people to ask questions. So feel free to reach out to me. And I see there's one question here. Yes. So how does this work with hybrid sessions? Is there someone post the question in chat, or do you ask the question or audio? Yes, go ahead. Please ask the question. So I find out the question. Okay, so I understand that you'll type the question in the session. So yeah, please go ahead and type the question. And while we're waiting for the questions, yeah, please do. If you have any comments on what your background is, what interested you in this session, how is this different from R2RML? That's a great question. It is not very different. Conceptually, it's not really different from R2RML. R2RML does exactly this. It says, I have my data in a relation table. And so let me actually, I don't know whether everyone saw the question. The question is, how is this different from R2RML? And the answer is really not fundamentally different at all. Conceptually, it's the same thing. You have your data in relation tables, and you want to create a graph from it. R2RML allows you to create an RDF graph from it. It's exactly the same thing. So it's not that these are really new ideas, but what is somewhat new is this whole debate around, okay, do I need to have a native database, or can I work with relational databases? And that's what I was trying to address. But it's the same thing. I used the property graph as an example for the most part. I could equally have used auto RML as an example, and it's really the same thing. But the point always is, yeah, keep in mind that I think the your source data is almost always in a relational database. So you can use either auto RML technology to get a graph model out of it, or for property graphs, some of the new SQL syntax that's coming up, or the PGQL syntax that we have to create a graph. So either way, so it is like auto RML. Other questions, comments? I will also welcome comments on what interested you in the session. In the sense of what, why you thought of attending the session as well. Oh, good question. Yeah. You mentioned that the results of the poll were 50-50. Would you assume to get different results from a different community, and were you surprised about the results? I wasn't too surprised about the results. Or maybe I was a little surprised. No, I would say I was not too surprised. And you're exactly right. I think we would get different results from a different community. So I don't know how widely spread this particular poll was. I don't know who all voted for it. Like, we definitely did not do any kind of campaigning for it or anything like that. I happened to see it, and I put in my vote. I do not know if you asked a lot of our customers who had not heard of this poll. I checked later; they had not heard of this poll. If I think the results might have been different. So it's not really I guess it's not a scientific poll in the sense that the sample size. I'm not sure how the word was spread, how they spread the word about the poll. So I wouldn't say the results surprised me, but what did surprise me or pleasantly surprise me is the amount of theoretical work that's gone into understanding these questions. I'm really coming at it from the business side for the most part. That something has to be really easy to learn, and something has to be integrated for it to have wide adoption. The debate, if you visit the website, contains a lot of information on, let me move to the side, has a lot of information around different techniques, different papers that have been written on the topic, which I thought, where did I have that? Which I thought was quite interesting. I thought that was interesting, and I haven't read all the papers yet, but it's clearly not just the business community, but the academic community also has these questions, and I've tried to answer these questions. So I guess that was a surprise. Any other questions, comments? So if not, I guess we can wrap up the session. And once again, thank you very much for attending. I really appreciate your time here, and look forward to connecting with you at other events or later in this conference at other sessions.